Okay, let's do test 4 review. This test uses a lot of conservation of energy. So you're going to want to know potential energies, uh, kinetic energies, linear, rotational kinetic energies, using total energies. Not a lot of friction. So I don't know how much friction is in there, but I don't think very much. So at least that's nice. Okay, so let's talk about a very simple object. The most simple object traveling in a circle would be a mass. For whatever reason, it's going around in a circle around the center of the circle. So what is the moment of inertia for that object? That is this. One mass, one radius. Okay, so nothing in between holding it there. No structure. It could be a magnetic field. It could be whatever. It could be all kinds of stuff. Anyway, something is keeping it in that circle. We could have many masses and many radii. Then we would be doing a sum of all the masses, adding the or multiplying them times the radius squared, and adding them all up from I equals 1 to n. That would give us a total of all the moments of inertia. And there's another way that we can do that. If we don't want to do sums, we can do the integral. So we can do the integral of those same things over the entire object or system if they aren't discrete, right? If they're discrete, that means, like, I don't know, maybe there's a whole bunch of beads like this on a circle. But if they're not discrete and it's one big old hoop, right? It's a big hoop all the way around, then we would integrate. So discrete bodies, this would be for discrete bodies, and this would be for solid objects. Okay, that's moment of inertia for you. So let's go on to our next topic, the parallel axis theorem. Okay, so let's say we have a rod. Here it is, and it's got some length L. If we have a center of mass here, and we have L over 2 from there to the center of mass, and we say that we have our first axis around the center of mass, so there's axis 1, and we do another axis here, axis 2. Okay, so erase a little bit there. We're rotating about axis 1, all right? So we're going to start with axis 1. The ICM is the moment of inertia about the center of mass. So for a rod, you can look it up, but ICM is equal to 1/12. 1/12. The mass of the object times the length of the object. Okay? Now we want to find the moment of inertia about axis 2. Okay, so this is how we do it with the parallel axis theorem. So I around axis 2. Well, that's going to be equal to the I center of mass plus the mass of the object times the distance from the center of mass axis to our new axis. So D equals this distance here. Okay? It equals the distance from center of mass to new axis of rotation. All right, so we're going to put in what the I center of mass is. That's 1/12 ml squared. And then we're going to add in our mass times our distance squared. Well, our distance is L over 2. So we're going to square L over 2. So we're going to get L squared over 4. And that's our new I about axis 2. Okay? And we're going to do that, add them together, common denominator of 12. That gives us 3 times 4 is 12, so we have 3/12. So let's pull out the ml squared. We've got 1/12 plus 3/12. And that's our new moment of inertia about that. So the parallel axis theorem allows you to get a new moment of inertia based on the moment of inertia about the center of mass axis. So we're going to go and do 1 plus 3 is 4. 4 divided by 12 is 1/3. So we end up with our A around axis 2 is equal to 1/3 ml squared. And there you have it. So that is an application of the parallel axis theorem. Okay? And if you go and look in the book, you'll notice that this is exactly what figure, I don't know, what is it? Whatever that figure is that does all the moments of inertia. That's the right answer. Okay? So did they use the parallel axis theorem to get that answer? Probably. Okay? So good job there. Now, let's talk a little bit about torque. So torque, what do you know? Torque is a vector. It equals I, which is a scalar, times alpha, which is a vector. Now, we've already talked about the directions of vectors. So if alpha is going in this direction, then alpha is out of the page. Okay? If alpha is out of the page, then that means that the torque has to be out of the page because they have to be in the same direction. Okay? If one goes in that direction, the other one goes in that direction because all this does is scale it. Okay? It's a scalar. That's it. All right. So that's for directions. We could do into the page too. Just so you're aware of that. All right. Now, torque is the analog to F equals ma. So that's the analog. This is the rotational analog of that. This is the second law. So second law, Newton's second law. This is the rotational analog of Newton's second law. All right. We also know that torque equals R cross F. So if we were to apply a force in this direction and we give this some radius R, then we would have our force cross F. So you put your fingers along R, you curl them to F, and your thumb should point into the page. Okay? So our situation gave us an into the page. Now we could do it the opposite and go the other direction completely. There's our R, here's our F. Our alpha would be here, and our torque would be out of the page. So torque equals R cross F. All right. Now, that also equals R, F, and we can take their magnitudes and multiply that by the sine of theta. This is going to give us a torque in this regard, and then we still have to figure out the direction. Okay, so this bit is scalar, and we need direction. However, we can still do our easy R cross F thing and get it. So let's say that we get direction from right hand rule. Okay, so that's the magnitude, then we get the direction from the right hand rule for the vector. Nice. Okay. Rotational motion and power. So power equals our work divided by time. You could say also energy, right? An energy per time. And if we want rotational work, then we can say we know that the rotational work is equal to our torque times our rotational distance. Just in case you guys were wondering, this has to be in radians. All right, your angle has to be in radians. You can't multiply by an angle. You need to work with radians. So since this is the case, let's rewrite the equation. Work, we can put a little rotational there, is equal to torque theta. Then we want d work. Well, that's just our torque times d theta. And that allows us to get our power, which is our d work divided by d time. Okay? Instantaneous power. All right? We could do averages by doing the differences between the work energy and the difference between the time. Or we could take the derivative of this guy and get it. So our power then is equal to our torque times d theta dt. Well, we know what d theta dt is, right? Everybody's screaming, that's angular velocity, angular velocity. You're screaming. You're saying, omega, omega. Yes, it's omega. And it's a dot product because that's in a direction, that's in a direction. So our dot product makes it work. All right. They're going to be in the same direction. They're either going to be into the page or out of the page. It could be that one's going one way and one's going the other way, and then you end up with negative power because your torque, you're really finding the power due to the torque. And if the torque's going the opposite direction of the omega, then your power is going to go, it's going to end up being negative because you're fighting the situation. Anyway, whatever. Chances are you're not going to see that, but that's true. Okay, so let's move to static equilibrium. All right, what does it mean to be in equilibrium? There are two conditions for equilibrium. The first condition, the sum of the forces, or F net, equals the sum of the forces. All of those forces, so we could say I equals 1 to n for all the Fi's. That has to equal, we know it equals our A for the center of mass of the object, but it has to equal 0, which implies that our A for the center of mass of the object is 0. Okay, so that is our first condition of equilibrium. All right, you can either say this, or you can say this, or F net equals 0, however you want to say it. All right. Then, our second condition is our torque net. And that is equal to the same thing, I equals 1, but for torque. Okay? And of course, that's got to be equal to I alpha. And that all has to equal 0 as well, which implies that alpha equals 0. Okay, that's it. That's static equilibrium. You got to have both conditions to be static equilibrium. So, need both. One of them isn't enough. Okay? All right. If you do have both, you are in equilibrium. The system that you're thinking about is in equilibrium. And then you can do all the things that allow you to get to move forward to solve your problem, because then once you're in equilibrium, things are a lot easier. You can do things that are easier and solve problems nicely. Let's keep static equilibrium there. Okay, so now these guys right here, let's talk about that. If your ACM is equal to 0, that implies that V is equal to a constant or 0. Okay, that's an implication. there. Also, if that equals 0, then you guys get it. It has to be either a constant or 0. If you're moving at a constant velocity or a constant angular momentum, greater than 0, v greater than 0, but constant, is equilibrium. Okay? So, that's very important. All right. Having a massless beam is a nice thing. Basically, what are we going to do here? An example, kind of. So we have an example. Massless. I have something on my screen that I'm trying to get rid of. Okay, an example. A massless beam. Why would I want a massless beam? So I don't have to worry about the center of mass of the beam. It's just a rigid object that has a fulcrum. So that's nice. What is the fulcrum? A fulcrum is simply just the pivot point. Okay? That's the pivot point that it would pivot about if we allowed it to move. Okay? Are we going to allow it to move? No. We're going to put force 1 down there. This is R1 to the pivot point. We're going to put force 2 here, going up. And there's R2. And then we've got force 3 acting here at this end, force 3. And of course, the distance from there to there is R3. Okay. Now, if it's actually rotating, okay, the thing is actually rotating about this pivot point. We are not in equilibrium, okay? We're rotating about this pivot point. Actually, let's put it here. We're rotating about that pivot point. So, if that's the case, we only get the one pivot point, okay? Because we're rotating. However, if we're not rotating, we get multiple pivot points. So hopefully we are in equilibrium or static. So you could call it static or in, that's a terrible or, in equilibrium. Static or equilibrium. We're there. All right? We can make our pivot point anything we want. To solve the problem. So we've got our massless beam. We are rotating due to these, we're not rotating. They're completely balanced, but we've got all kinds of forces happening. We've got F1, R1, we've got F2 and R2, and we've got F3 and R3. So torques, oh gosh, excuse me, torques and forces are all rotating, okay? All right, so we can move that pivot point anywhere we want to solve the problem. So that's nice. We can choose any point. We could choose the point at F2. If we want to make our pivot point here, that's great. And then we can apply all the torques. Torque F1 is going to be R2 plus R1 times F1. And then torque F3 is going to be R3 minus R2 times F3. So we can do that. It's nice to know, and it's a very handy way to find out torques and forces and get everything that you need. Okay, let's move on to angular momentum. Angular momentum, we all know it. It's L. It's equal to I omega, and it's the counterpart to linear momentum. So it's the rotational analog to linear momentum, which is P equals mv. Okay, this is linear. And this is rotational. And we're talking about rotational stuff, and we're going to end up using it. What are the... oh, you know what? When I was talking about torque earlier, I didn't mention... I didn't mention the units of torque. Let's do that. Units real quick. Torque is equal to a meter Newton. All right, think of it as a meter Newton, like a foot-pound. Okay, meter Newton. That's torque. It is not a Newton meter, which is a joule. Okay, it's a meter Newton. It's just torque. Okay, let's go back down here then to our angular momentum. This is not as easy. It's a kilogram meter squared per second. Okay? When you go through and you analyze the units, that's what you get. Fine. No big whoop there. It doesn't have... Nobody came along and called it Poisson's whatever, or... I don't know. Who would they give angular momentum to? I don't know. Anyway, it's just kilogram meter squared per second. So, there have to be two conditions for equilibrium. Okay? So the first condition we already talked about was our F net equals 0. Our second condition was our torque net equals to 0. So this torque net, force net equals 0 gives us delta P is equal to 0. Because normally the impulse force equation, delta P is equal to our force times time. All right? But if all the forces are 0, we get this. Well, what does that imply? That implies that our final is equal to our initial momentum. So this gives us linear conservation of momentum. Cons of momentum. All right. This guy, same. Delta L is equal to torque times time. All right. And since we're equal to 0, this equals 0, we get delta L equals 0. And what does that mean? That means L final equals L initial. And we are now looking at conservation of angry mom. No, angular momentum. All right? Conservation of angular momentum. Conservation of linear momentum. One requires one condition for equilibrium, one requires the other. Okay. Impulse equations. Well, I wrote them. This is the impulse torque equation. This is the impulse force equation. Okay? So rotational impulse is this, and it happens to equal our torque times time. Now you could, times the delta t for the delta L, but you could say that then our torque is equal to, I don't want a delta. The instantaneous torque would be dL dt. All right, the average torque is equal to delta L over delta T. Okay? All right, and the same thing goes for forces, right? Same. It's just you're dealing with momentums instead. All right. We're doing great. Everybody happy. We're going to start with a new situation. We're going to deal with a plane. We have some angle, and we've got a can rolling down the plane. It has some height. When it gets to the bottom, the height of the center of mass is this right here. So that's nice. We've got a V initial equal to 0. We've got a V final equal to V final, whatever it is. In fact, we're probably going to, what am I going to do? Am I going to figure out what V final is here? Let's look. Yeah, we're going to figure out what V final is. Okay. So, we are going. So this is part of the conservation of energy that I was talking about earlier. Cons of energy. We're going to use that. Oh boy. Look at this happening. Use. Okay, we're going to use conservation of energy, all right, to find out what V final is. So conservation of energy means E final is equal to our E initial. Our initial energy total is our mass of our object. We'll just put a little mass here, times gravity times h. All right, keeping it easy. Our E final, we're going to have kinetic energy, but we're going to have linear kinetic energy, and we're going to have rotational kinetic energy. I'm going to rewrite those as KEV plus KE as a function of omega. So we've got it as a function of velocity and as of omega. Well, we know velocity is 1/2 mv squared, and we talked about this up higher, and we know that this is 1/2 I omega squared. So that's our E final. Now we just need to know what the I for a cylinder is. So let's write that out, I cylinder. And that equals, oh, you want to keep writing down there, and I don't want you to. Okay, 1/2 mr squared. Great. Now, here's the trick. V squared equals r squared omega squared. All right. So we're gonna do E final is equal to 1/2 mv squared, straightforward, plus 1/2. Now we're going to insert 1/2 mr squared, 1/2 mr squared, and then that's times omega squared. But if we rewrite it without these guys, we'll notice that this and this is our velocity squared. So now we've got 1/2 mv squared plus 1/4 mv squared. Nice, right? We can factor out the mv squared. We've got 1/2 plus 1/4, that's 3/4. And now we can equate this with this. So initially we have mgh. Finally we have, well, let's do our 3/4 first. 3/4 mv squared. All right, and we're looking for v. So we want v, our velocity at our final velocity. Let's put a little f down there. And nice, this cancels with this. We've got v final is equal to 4/3 gh, and we're going to multiply or take the square root of all that. Great. I think that does it for that problem. If you notice, v final is not a function of the mass. It's not a function, so not included. We don't care about the mass. We don't care about the radius of the object, right? We don't care about the length of the object. It could be this long. We don't care about that length either. So all we need is the height above where we're going to measure the v final. So not included, but the height and gravity are needed. They're required. Okay. Let's do a little bit more on angular momentum. Let's talk about more angular momentum. Oh, I kind of already did that. I did that. Okay. I did that, so let's just do gravity. Oh. It's weird that it erased and moved my page all at the same time. Okay. Gravity. What are we going to be working with? We're classical physics. We're going to be working with Newton. Newton's universal law of gravity. Newton's universal law of gravity. What is it? What is it? Okay. So F12 is, let's draw out two objects. We've got mass, I'm going to call the big mass 2 and the little mass 1. Okay, and they are attracted to each other due to their masses. Just due to their masses. We're not going to talk about how the masses are warping space. We're just gonna say that this mass wants to be they're attracted to. So this is the force of 2 on 1. This is the force of 1 on 2. Okay? Great. The force of 1 on 2. Let's get into it. We've got the mass of 1 times the mass of 2. And in my coordinate system, I'm actually calling this positive. Okay, so we've got mass 1, mass 2. We've got the distance between them. So we're going to take R12, we're going to square that. We're going to multiply the whole thing by g. And that is in the direction, the r hat direction of R12. Fine. Good. That happens to equal minus F21. Okay, so here's the scene. Here's the situation. We've got F equals ma. So there's Newton's second law. Because our A is g, which happens to equal m2 over R12 squared times g. All right? So we've got our F where that equals A. So F equals ma. We have inertia. We have Newton's first law because inertia, the larger these objects are, the less they're going to want to move. So inertia is part of the situation. Inertia. So we've seen the second law, we've seen the first law, and here, when we're writing it in this regard, we're noticing equal and opposite. So we're seeing Newton's third law. And it's a statement of Newton's universal law of gravity. So we are also seeing Newton's universal law of gravity. NULGE. I've never done that acronym before, but it's gross. Okay, but the whole thing is the statement of Newton's universal law of gravity. So really, it sums up Newton's work completely. Let's talk a little bit about G. What does G equal to? It's 6.67. I don't know if I give this to you on the test, so you might want to have this written down in your cheat sheet. Newtons meters squared per kilogram squared. All right. This is the universal gravitational constant. All right, and it is still to this day the universal gravitational constant. We still use it. All right, even with all of our relativity and all those other things that we aren't talking about in this class. Okay, let's say we have Earth, okay, and we want to be near Earth's surface. Well, if we're near Earth's surface, how far away are we from Earth's center of mass? We are the radius of the Earth. Here we are on the surface, we're the radius of the Earth away. So our force of gravity is going to be equal to our object, whatever we're worried about. The mass of the Earth, the radius of the Earth squared times g. All right? Well, we already know that that's equal to the mass of the object times g, right? So on Earth, if we're on the surface of the planet, this bit equals g. Okay, so the mass of Earth divided by the radius of Earth squared is equal to g if we multiply by our gravitational constant. Okay, now we can figure out g for other planets. Sure, we can do that. And then we would just use that other planet, like Mars or whatever, the moon. So then we would just have the mass of the moon or Mars and the radius of moon or Mars, and we'd be multiplying by our gravitational constant, and that would be g for that planet or that celestial body, right? It could be a star, who knows? It could be all kinds of stuff. Good. Now, we went through, hopefully you saw the videos, I hope, for gravity. And you'll want to watch them if you didn't, but I'm going to sum up what we found. So, what we found was g is a function of r, okay? And that means that whatever the mass of the object in question is, divided by the radius squared times g, this is the function, okay, for the gravitation at any place for that object. So, what does that mean? We're going away. R is the distance from the center of mass. And I wrote max, but I meant to write mass. All right, distance from the center of mass. So, do I want to write? Yeah, I'm going to do it. I didn't do it in the notes, but we'll do g of r for a body. Here's our radius going out that direction. Here's the radius of the body. And if it's homogeneous, okay, we're dealing with a homogeneous body. I talked about inhomogeneous in the lectures, okay? But we're going to deal with just a homogeneous body. We're going to max out at this distance, okay? And since it's homogeneous, I went through and figured out for you guys that g on the inside of the object, it's linear for a homogeneous body all the way up to a maximum at the surface of the planet. What was that equation that we came up with? G as a function of r, I'm going to write in down here so you know that we're talking about the inside. That's 4/3 rho. That's rho is the density, homogeneous density for the planet or object or whatever. Okay, pi. And then we're going to multiply by r inside, and then we're going to multiply by our gravitational constant, and that's in the r hat direction. Okay, this is on the inside. So this our slope of the line, let's move up a little bit. the slope is equal to 4/3 rho pi g, okay? And then we've got r, so y equals our slope times r, and we don't need to add a b because we've got no offset. This is at 0. So that's our slope, okay? All right, so that's on the inside. All right, but on the outside, we have the same old thing. We have the same old thing. G of r on the outside is going to be equal to our mass of the object divided by the radius of the object squared times g. All right, and that, of course, is going to be going in the r hat direction as well. So we can stick a little vector on these guys. And if you do a graph of 1 over something squared, you go like this. And why did I say r of the object squared? I don't know. That's not correct. It's your radius away from the center of mass squared. Okay, so let's call it r out. R out is equal to r for the object plus r above the surface. Of the object. And I'm going to, instead of calling that RB, I'm going to call it R object. All right. Good. There you have it. What else? What else? Okay, escape velocity. Escape velocity. Here, this really tricks people up. Trips people up a lot. So we need to, we're going to go over it one more time. Here's an object, sun, moon, earth, doesn't matter, some celestial body. Here's another object, satellite, something small, okay? Now imagine it's infinitely far away, okay? At this point, radius is equal to infinity from the center of mass of this object, okay? So it's equal to infinity, all right? At this point, it's this point that you compare everything to. So let's do our E initial, all right? Our E initial at this point is 1/2 m. So this body, I don't know, let's give it a velocity in this direction so that we bring it in closer eventually. So it's got that, and then its radius is at infinity. So 1/2 mv squared, what I'm saying is v is greater than 0. Okay. We're going to be subtracting. Here's big M. This is little m. M big M over R naught times G. And this is going to equal our KE final plus our potential energy final. All right, but let's just talk about these guys a little bit initially. If this is infinity, if this guy is right here is infinity, what does that make this term? Well, other than undefined, because you're not Chuck Norris. You can't divide by... Oh, wait, no, Chuck Norris can't divide by 0, but he can divide by infinity, and that means 0. Okay, so you, me, Chuck Norris, we've got this covered. It's the 0 he can do that no one else can. Okay, so 1/2 mv squared is going to be equal to this stuff here. But our potential energy, no matter what happens, is going to be less than this at all times. So our potential energy maximum is 0. That means any other potential energies that we have, anytime we're down in this range, our little guy is down here with some radius less than infinity, this potential energy has to be less than 0. Less than 0 means negative, okay? So no matter what happens, this is a negative number. So we're going to say that 1/2 mv squared up here, whatever this velocity happens to be, that's our initial velocity. We're going to subtract off 0, so I'm not even going to write 0 there. That's our 1/2 mv final squared minus, has to be minus, we are never going to get above 0 for our potential energies. All right, so it has to be minus, and then we're going to multiply our mass times our big mass times G over our final radius, okay? And our final is less than infinity. So this equation is what you would have. The only way to make this term positive is to move it to the other side of the equation. Then we could do something like mg over rf is equal to 1/2 m v final squared minus v initial squared. Okay, guys? All right. Now, what if we want to do escape velocity and we really, really want to know, we're going to run this whole thing in reverse, okay? We're going to start out here at this point, and we want to know, in order for this object to get to this point with 0, v final equals 0 velocity, but it escapes. It gets to r equals infinity. We don't care what the final velocity is. We just want it to be there, okay? So in order for that to happen, we are now trying to escape the situation, all right? For us to do that, we are going to run this whole thing in reverse. So we've got 1/2 mv squared equals 1/2 m v initial, this would be final, v initial squared, it's a big V, or not a big V, but you know what I mean. Okay. minus m g over r initial. So this is our initial side. This is our final side. But we just said that v final was equal to 0. So that means that this and this guy are equal to each other because they equal 0. So we're going to rewrite it as 1/2 mv initial. But instead of calling it initial, I'm going to call it escape, because this is the velocity that you have to escape the situation. So v escape is equal to our big M g over our initial. So we can cancel some stuff, we can multiply by some stuff, and we can figure out our v escape velocity is equal to 2 times our big M g over our initial radius. Did I drop a squared? I did. Yep. Very nice. Very good. Okay, that's our escape velocity. All right, one last little bit and then we're done. What do we need? We need to talk about orbits. So, in the lectures, I showed that the orbit, our velocity in orbit, is equal to the big mass of the object holding us down or holding us attached to it squared. All right? And we also know that omega is equal to our velocity divided by r. So we could think of this as the large mass. We could have a little guy out here doing something. Let's say it's going in this direction, and it has a v orbit which is linear. Right. Here's our object. Okay, so omega is then equal to 1 over r times capital M g over r. And what we could then do is take that and move that r onto the inside of our radical, and we'd have mg over r cubed. Okay? So if we wanted omega for this situation, this is what we would have. If we wanted just the velocity, this is what we would have. And of course, we don't want to forget that our t is equal to 2 pi 1 over omega. Our frequency is equal to 1 over 2 pi omega. And that would mean our period for the orbit is 2 pi times r third over mg square root. Of course, the frequency is 1 over that. So we have 1 over 2 pi mg over r cubed. square root. So that's it, guys. Good luck on the test.